All right, so what you should have seen yesterday, if you watched the video, is you would have seen now how we're applying 2 dimensions into forces. So we're no longer dealing with forces that are purely left and right, or forces that are purely up and down. We've now got a combination of the 2 of them. And where this all comes together is inclines. So what you've seen before, if we've got, say, a ball sitting on a level surface like this, what are the forces acting on this ball? Force normal. Yeah. So yeah, we got force of gravity going down. We've got force normal going up. These 2 are balanced. Yeah? What's that?
Why did we start with the force of normal? Why did we start first?
It doesn't matter which one you do first. So whether you put this one first or you put this force first, it doesn't matter. They're both acting at the same point. So these are the 2 forces acting. Because they are balanced, we have no net force. So that means that our acceleration is 0. It tends to stay at rest because we have no unbalanced force, so it stays at rest. However, if we take a ball and we put it onto an inclined plane, so we just have something that's at a slant, this ball now is going to roll down the hill. Even if you're not applying any force, just by having this inclined, it'll start to roll down. So what the forces look like in this case, we still have force of gravity acting straight down, but my normal force is going to be different. It's not pointing straight up anymore. So do you remember the definition of a normal force? Very few people do. So normal force is your force applied by a surface and it's perpendicular to the surface. So everything on the desk and everything we dealt with last year, you're on a level plane. So the normal force is always up. Whereas with an incline, this force has to be 90 degrees from the surface. So this is what my normal force looks like. It's now at an angle. Notice if I were to extend this down, here's my 90 degrees. So that's where it comes from. It has to be perpendicular to the normal force. That's where I get it. I don't want that there. But that's where it comes from. So from this, we now have a portion of our force of gravity that's causing this object to move down the slope. So this is what is happening here. We've got some net force that is acting down the surface. I'm not going to show it on this one, but we'll show it a little bit later here. These are not equal because we're going to have some acceleration. If you've ever had a ball that's on a hill, it starts to roll. This means that my forces are not balanced. So if I extend this, so here's the graph we just drew, just flipped a little bit. So even though Fg pulls straight down at all times, only part of this is going to be our normal force. So what I'm going to do with this is I'm going to break up Fg into 2 parts. And now my normal force is going to be equal to this portion of Fg, and this part here is going to be parallel to the surface. So this is the confusing part, and this is what we're going to need to adjust with this, yeah. So what we're doing for this is we are going to change our coordinate system. So you've always seen us break things up into this coordinate system. We've always broken things up into x and y component thus far. However, in dealing with an incline, this is going to be problematic. Because is the x component of the force causing it to go down the hill or the y component? You can't tell, because it's going to be a combination of both. The part that's pulling it down the hill is this. So that's a mix of both x and y. So what we're going to do in order to figure this out is I'm going to tilt my axes. I'm no longer going to deal with x and y. I'm going to switch this instead, and I'm going to tilt these axes so that I'm going to deal with a part that's parallel to the surface and a part that's perpendicular. So if this is my surface like this, I'm going to change my coordinate system. So now I've got a part here that's, I'll write it out first. So parallel, perpendicular, I might have spelled that out wrong. So parallel, perpendicular. This is now going to get us what we're looking for as far as our the forces go. So I will often write this as parallel with a double line like this, and perpendicular as an upside down T. These are just the general formats for how you write that. So the reason why I want to write this out like this is because which direction, if there's an object here, say, what direction is that going to move in terms of our coordinate system? I've got hand gestures. So it's going to go down the slope, right? Which is in the parallel direction. So any force that is parallel is going to cause the object to move down the slope. Any force that is perpendicular isn't actually causing movement in my object. So we can actually still consider this if we look at different objects here. So let's say I took my calculator here and I have it on a surface, right? So I'm still dealing with parallel perpendicular if I'm dealing with something horizontal, but I also can say it's x, y. So if I push down on this, is anything going to happen for movement? No. Why? It's not moving, but why? Yeah, so what direction am I pushing in this case? Downwards, which is in the y direction. Can my object move in the y direction? No. Whereas if I push this way, it moves. Because I'm now pushing parallel to the surface, which is the same thing in this case. So I'm pushing in the x, I'm pushing in the parallel. In this case, I don't have x and y. So now I've got it slanted. Let's do it so that it's not actually falling. So it's slanted. If I push in the y direction, which is straight down, it moves. If I push in the x direction, it moves. So part of the x direction is parallel, part of the y direction is parallel. So this is why I need to break it up into parallel perpendicular, because if I have it like this and I push perpendicular, does it move? No. So if I'm pushing into the surface or out of the surface, it does not move. If I push parallel to the surface, then it's going to move. So we were actually dealing with this last year, except we were calling it still x and y, because they're both the same. But as soon as I tilt my incline, I'm no longer just dealing with x and y, I have to deal with parallel and perpendicular.
So inclines are all parallel perpendicular, they don't have x and y?
So this we're only going to deal with parallel and perpendicular. There is still, yeah, with the inclines. There still is x and y, it just won't help us in this case.
I also don't understand the shape. Where's the ball?
So the ball is here, or the box is here.
And what's the arrow? What is the focus?
Yeah, so we've got our normal force, we've got a force of gravity. Because the force of gravity is part parallel, part perpendicular. So this is what we're going to do every single case. It's not just for you to see it here. We're going to have to split this up into its parallel and perpendicular. Just like when we dealt with kinematics, we always broke up every single vector that's a combination of x and y. We had to split it up into this is the x component, this is the y component. So now with inclines, we're going to have to split up everything into a parallel component and a perpendicular component. So this would be FG parallel, and this is going to be FG perpendicular. So whenever we're dealing with inclines, we now need to split it up into parallel, perpendicular. Parallel to the surface.
So relative to the surface, not the y.
Correct, yeah. So my parallel is parallel to the surface. My perpendicular is perpendicular to the surface. So we're always going to be dealing with parallel and perpendicular, no longer x and y. That's essentially what I talked about here. So when I'm splitting this up, so let's say this is FG. Like I said, we need to split it up into our x and y components. And what you're going to want to do, so we split it up like this. So this one's the parallel, this is FG total, this is FG perpendicular. And then force normal sticking out like this. The question becomes, if this is theta, where's theta in this triangle? Downwards? What do you think? This one? Okay. So I've got someone saying this one, I've got someone saying this one. Yeah. This one? This one's for sure is 90 degrees, because parallel and perpendicular for sure state that those have to be 90 degrees. How could we figure this out? Because guaranteed most of you are going to get confused on this on the test. It will, but we're looking at because often you're just going to be given the angle of your incline. So we want to know where is that angle when I'm splitting this up. Because I'm going to need to use sine and cosine to get parallel and perpendicular. But I need to know where do I get this. You think it's up here? Okay, so let's try and figure this out. So if I'm doing this, don't draw this in your triangle because it's going to get messy. But just watch as I'm doing this. So notice here, I've got a right triangle. Right? So if this is a right triangle, what is this angle here? If this is theta, what's this one? No. You don't know this is 45. 90 minus theta. Right? If this is theta, this has to be 90 minus theta. If this is 90 minus theta, notice what I've got here. What's this? My Z rule. So what does that mean this angle here is? So this one has to be 90 minus theta. And here's another right triangle. So what does that tell me this one has to be? So this is a long convoluted way to get that this one up here is theta. That's the proof of it. If you want to just remember, if you set up FG perpendicular and parallel like this, where it's inside of my incline, it's always going to be the top one. If you decide to set up your triangle the other way, where I go this way and this way, this is theta. So it depends on how you set up your triangle. Instead of trying to remember how to do each of these, you don't have to do that. You can just memorize which one it is. That's going to be quicker. I wanted to show you the process so that if you ever get lost, you can at least hopefully maybe remember that. But essentially, you just need to remember if I set up my perpendicular first, then my parallel, the angle's at the top. Because that's always going to be the case. So let me erase all of this so it's less confusing. So all you need to remember from all that is this angle here is theta. The one at the top, as long as you set up your triangle like this. No, because if I did it this way, it's down here. Yeah, I mean, if you want, you can always memorize as well. It's always going to be the angle beside the perpendicular component. You could memorize it that way too. Since my perpendicular is here, so the angle is here. My perpendicular is here, so the angle is here. There's just a few ways you could think about that. I'll leave this one, because that's at least a little bit less confusing. So a few things to notice with this. So which portion of the force of gravity is causing the object to go down the slope? Is it the perpendicular or is it the parallel? Mustafa? Put it away in your pocket so I don't see it again. Thank you. My parallel. The parallel one is what's pushing it down the surface. So only the parallel portion of force of gravity, what do I want to say? Let's say FG parallel. So only FG parallel pulls down the ramp. Okay? What is the FG perpendicular doing? So it doesn't move it, but what is it doing? Because it's doing something. It's equal and opposite to the force normal, yeah. But what is the force of gravity perpendicular actually doing to the object? Physically, what's it doing? Yeah, it keeps it from flying off the surface. So the FG perpendicular is what's holding the object to the surface. Just like if I've got something on the desk, FG is causing it not to float. If you don't have FG, it's going to float. If you don't have FG perpendicular, it's going to float off of the surface. So the FG perpendicular, as Nazar said, so it is going to be equal and opposite to the normal force, which is what we're going to need to deal with for lots of the questions. So FG again, I'm not 100% sure about the spelling on that, but the perpendicular, always equal and opposite to, it's not always equal to this. But in this case, FG perpendicular is equal to the normal force. There are cases where they're not going to be equal, and that's if you have another force pushing down onto the surface. But we'll deal with that at another point. Because these two are opposing each other, right? They're pushing in opposite direction. So your object is not hovering above the surface, it's not going into the surface, so these two have to be equal. Otherwise, there'll be an unbalance in that area and it'll float or go into the surface. Got a question? Okay. Yeah. Mm-hmm. Well, all the forces into the surface are always going to equal the forces out of the surface. So if I add another force, either pushing into the surface or pulling out, these two are not going to equal each other. So it depends on if there's another force. But if an object stays on the surface, the forces going into the surface must balance the forces going out. So in our case, this works. It won't always work every time. In general, this is mostly going to be the case. But if I add extra forces, it might not. So let's give some of these a try with actual numbers. I think I'll be good not zooming in. So we've got an 8 kilogram block sliding down a frictionless inclined plane. We want to know what is the acceleration. So as with last year with forces, drawing a free body diagram is the best start to what we're doing, because then you can see what's going on. So here, I'm going to draw it on this side. Here we got Fg. Here we've got our normal force. If I want to solve for acceleration, any guesses what equation we're using? Yeah, so we're dealing with F net equals ma. What is my F net in this case? No. FG parallel, right? So we need to split this up. I've got FG parallel. I've got FG perpendicular. The force normal and the FG perpendicular are equal, so they cancel out. And I get that my net force is just simply FG parallel. Hopefully when you read this question, you saw the word frictionless in there, and your brain's already starting to think about what happens if this is not frictionless, which will come in a little bit. But we'll get there. So we've got mass, we know that. I'm looking for acceleration. How do I get FG parallel? Yeah, so we have the 35-degree angle. Perpendicular. Yeah. Yeah, so from this, I've got a right triangle, like so. I've got the angle. I want the opposite side. Do I know what FG is? Yeah, mass times acceleration due to gravity. So if I write this out, I get Fg times sine 35. Again, I'm just assuming you know I'm using SOHCAHTOA. I took that equation and just rearranged it. Of this? To this. So then I can figure out, I already know Fg, so I can plug that in. Ma equals mg sine 35. Notice with this, I don't even need the masses. They can cancel out, and it won't matter. So it doesn't matter what the mass is in this case. If you have no friction, if I have a feather, or if I have a, I don't know, 1 ton something, box of something, it's going to accelerate down at the same rate. Which intuitively makes no sense to you, but that's because you're used to a world of friction. But just a fun note, I can cancel out the masses if I want to. So plug in numbers for this. So 8 times A equals 8 times 9.8 times sine 35. Again, notice those can cancel. And you'll get some number for A. Like I've said before, I'm not so much worried about getting the final answer at this point. All the steps up to this point are what you need. By now you should know how to type in 9.8 times sine 35 in your calculator. Hopefully. Yeah. That's what I'm wanting to look for. So FG parallel is equal to this. So I times FG onto this side. I got FG sine 35 is equal to FG parallel. So I use substitution. Make sense? From this. So if I times FG onto this side, I get FG sine 35 equals FG parallel, which is what I have here. Because I'm dealing with sine theta equals opposite over hypotenuse. Sine 35 is opposite, this one, over hypotenuse, which is FG. It's just from this triangle here. Because why am I needing it? So with this case, we needed it because we wanted what's the F net equation. And F net is mass times acceleration, but it's also the sum of all the forces. So if I add all these forces up, force normal plus force perpendicular cancel out because they're balanced. So the net force is FG parallel. So since that is the only force that's left over when I add them together, that's the net force. Yeah, because we only want the one portion of it. We don't want the whole thing. So when I do FG sine 35, that is the parallel portion of FG. You mean which angle in here? So I knew that it was up here. This is what I had shown when I did this big long thing. So just... yeah, so whenever you're given the theta down here, you know it's either this one if you set up the triangle this way, or it's this one if you set up the triangle this way. So it's always going to be the case. Basically, in every question, I will tell you what this theta is. And you'll need to know how to apply that into your triangle here. It's just, commonly it's easier to measure what is this angle physically than it is to try and measure these angles. So just in general, that's how it's laid out. Yeah. When I combine tensions with this, yes. It's the last section, so it should be the hardest part. Yeah, you guys remember how much fun you had with tension last year, right? It's going to be even more fun when we add inclines. All right, any other questions with this one? Who's going to be at school when I do tension? Tomorrow is tension. On Wednesday is two objects with tension. So it's you guys. You both have review classes, but you guys get to be in class, and they get to be in class virtually by watching it online. The other option, I've thought about this, but I don't know how it would work, is instead of recording it and doing it online, to see for those of you who are not here, if I did like a YouTube live or something, if any of you would join in. Yeah, that's what I'm asking. If I do the YouTube live, I'm pretty sure I can post that video up afterwards. True, but there's less options with the Zoom calls and more complications than if I just record it onto my computer. Trust me, I've thought of all the different options. You mean setting it up the other direction? Like, yep, yeah, I could do that. All right, so let's move on. So I've got another object here. So I've got another object here. This time it's at the bottom. The great part is if I have to call out a student for talking in the middle of class, the entire world gets to know that you're talking in the middle of my class. So I suggest you don't. So how much force is required to push an 11 kilogram block up a frictionless ramp at a constant velocity? So what is something key that you notice in this question by reading it? That should automatically stimulate your brain. Yep. Frictionless. This is a great thing to notice. What else? Constant velocity. What does constant velocity tell you? No acceleration, which means all the forces are equal. So taking into account frictionless, taking into account constant velocity, we need to try and figure this all out. So like always, let's draw out all the forces. Fg, F normal. Where would I put the applied force in this case? What do you think? With the F normal? No. Parallel and going up the incline or down? Up the incline. So this is my force applied. So notice with this, I don't want my computer to go freezing. So from this, we now get our free body diagram. Now, I'm going to again split up Fg, and we're going to split it up the opposite way this time, just for fun. Just for fun, like I just said. Did you just say, can I skip the fun? Yes, I'd always skip the fun in this class. So this is how we split it up. Again, it doesn't matter if you do this first and then this, or this first and then this. I'll show you it doesn't matter. So when I set it up this way now, again, the angle needs to be with the perpendicular side. So this angle here is my 58 degrees. From this, I noticed, and the information given in the question, I can combine a few things. We said it's constant velocity, and therefore all the forces are balanced. So I can automatically write out two things. That Fn is equal to Fg perpendicular. So those are my perpendicular forces are balanced. And I can say that my force applied is equal to Fg parallel. So even though it's frictionless, there is still a force that's opposing the motion, or something that's slowing it down. We're looking for the applied force. So therefore, I just need to figure out what FG parallel is, which we've actually already done. Well, we did that in a previous question, I mean. So we've seen that already. So this is nothing that's overly new. So let's take this, and I'll get to your question in a sec. So again, because it's constant velocity, these two forces have to be balanced. Otherwise, we're going to accelerate. Given our triangle, I can figure out FG parallel. And I can do that because we've got our 90-degree triangle here. I've got an angle. I want the opposite side. So we put what the hypotenuse is times sine, because it's the opposite. I know FG is mg. And at this point, it's home free. You should be able to do this no problem if you can get to this point. 11 times 9.8, sine 58, and then you get what your force applied is. Again, some number. At this point, you can plug that into your calculator. All right, questions on this one? You mean in your final answer? So that's a good question. So do the directions matter with this? Yes, because forces are vectors, so it does matter the direction that it points. However, notice because I drew the free body diagram, you told me already the direction. So I'm going to mark the direction for the force applied based on what you show in the diagram. So as long as you draw this, I can tell the direction you're pointing. Any other questions with this? Make sense? You're messed up by which angle it is? How do you figure out which angle is 58? Just memorize it's by the parallel, or the perpendicular, sorry. Memorize that it's by the perpendicular, you'll always get it right. So notice here, the angle is by FG perpendicular. The angle here by FG perpendicular. So if it doesn't make sense where it comes from, I'll be the bad teacher and say just memorize it. Any other questions? All right, let's try this next one. I don't know, is this the last example? Yep, okay. Last example. So we've got a block sitting on an incline ramp. Now we've got a coefficient of friction. So we're going to have friction in this case. So starting things off, let's draw a free body diagram. We've got Fg. We've got a normal force that should be at 90 degrees. And what else do I have in this case? Yeah, I've got friction. And what direction is friction pointing in this case? Against the motion. And what motion is this doing? It's going to go down. So friction needs to oppose the motion. So it's like this. But this is a great question because we are going to get to a case where it's hard to tell where the friction is. So the fact that you said friction opposes motion is very key when we get to later in the unit. So this is a good definition to remember. Friction opposes motion. So whatever direction you have movement, friction points the other direction. So again, let's go back and let's split up Fg, because that's always a good place to start. When in doubt, split this apart. So I've got FG parallel, I've got FG perpendicular, and my angle is up here because we're beside the FG perpendicular. Because your object is going to accelerate down the incline. There's no force pushing it up, so intuitively the box has to go down.
So if it was going upwards like this one, the force of friction was going to go up.
Then, so if this block was pushed up, the force of friction would point the opposite way. Yeah. Like we solved all the other ones. So we want the block's acceleration, so any guesses what equation we're going to use? Yeah. So we've got F net. This is going to equal MA. But what is the sum of all the forces in this case? So what's the winning force? What's the force that's causing the option to move? No? Yeah. So the winning force in this case, or what's causing the object to move, is FG parallel. Minus my friction, yeah, because friction is opposing that. So this is my net equation. Again, do not memorize FG parallel minus force of friction is the net equation, because I can give you a bunch of cases where that does not work. Yep. Yeah, so it's sitting just meaning it's on the inclined plane, and then we want to find the acceleration. So we're trying to figure out what would be, what is the acceleration, implying that it does move. If we figured out, that the force of friction is bigger than FG parallel, it's at rest. Then it would be at rest. It's not moving. So that would be a nice trick question that I could give you, but I don't think I do. Yeah.
We're always going to use time to find
Yes. If I give you a different angle. Mm-hmm. Yeah. Are we supposed to use what, sorry? Units, yeah. I've only been putting the number sign here, but once you get the number, the forces are with newtons. Yeah. Yeah, that's right. Okay, so let's do this here. So FG parallel, we need to figure out what that is. So this is just going to be FG sine 40, because we have the angle, minus, oh, and we have to deal with force of friction now. So this is mu Fn. So here's the case where Fn is no longer equal to mass times acceleration due to gravity. So in our case here, what does Fn equal to? What's the equation it equals to? FG cosine. Yeah, how'd you get that? Yeah, so in this case, my force normal is equal to FG perpendicular. So this is because we're not accelerating up or down off the surface. It's just like this. So then in order to get that, here's where we're now going to use cosine 40. So Marwan, you're asking about this. When will we use cosine? It's in this case. Yep. That's why instead of trying to memorize when is sine, when is cosine, just remember this triangle. If you can remember triangles, you should be good. 40. Yeah, just the angle there.
So Sonia, is the number for FG prediction going to be so the last time of gravity will be the exact same last time of gravity for FG parallel?
Yeah, because the hypotenuse is the same for both. So yeah, this is FG, this is also FG. I just did this separately so I don't have to keep writing this equation all the way down. But I'll now get from this MA equals FG, which is mg sine 40 minus mu times Fn, and we just figured out Fn is FG cos 40. So mg cos 40. Do we have all these variables now? Do I have the mass? Yep. Do I have the acceleration due to gravity? Yep. Do we have mu? Yep. Does the mass matter in this case?
No, cancels out.
They all cancel. Yes. But notice I've got mass here, I've got mass here, I've got mass here. So if I divide every term by mass, they all disappear. So I don't actually need to tell you what the mass of the block is because it doesn't matter. And this is even a case with friction. So even when you do have friction, it still doesn't matter what the mass is. So now you can solve this. Acceleration is 9.8 times sine 40 minus mu, which we said is 0.21, times g times cos 40. So again, once you get to this point, you're just plugging this all into your calculator. So you can get whatever your final answer is. Yeah?
Not that if I just cancel out the mass.
No, you'll get the same answer. Because notice what you'll do here is you'll have 15 times all this minus 15 times all this, and then you're going to divide by 15. Okay. Yeah, you don't have to cancel out the masses if it messes you up. Any other questions of this?
Does it matter if I solve for x in the g pyramid and then write the number because I did that, and I got a negative number, and then I put 9.8 cosine 40 and I got
Oh,
I actually got a number for
you got a negative number for this?
No, I got a number, a number.
Yeah.
When I put it in, like, the 5 and 3, and I got a negative number.
For your acceleration?
Yeah.
You shouldn't.
I know, but when I put 9.8 here, I got a good number,
Because you then need to times it by 0.21. But, no, because we already took that into account when we subtracted. Are you in degree mode or radian mode? .72 times or meters per second squared. Well, if you did it your way, it would still work. It should still work. It shouldn't. Because what?
We also
No, it shouldn't make a difference. Well, I'm going to stop the recording here, but then we can